Hello, and welcome to Deep Space Sleep, a quiet place to slow down and drift through real cosmic events with a calm mind and a steady pace. Tonight we are going to follow a story that begins far away on the surface of the Sun and ends here around Earth in the invisible space where satellites move. Radio waves travel, and the planet's magnetic shield quietly does its work. The headline sounds urgent, almost like a warning siren in a world that usually feels insulated from the sky. The Sun has just fired a coronal mass ejection toward Earth, and we want a timeline of impact. But the truth is not a single dramatic moment. It is a long sequence of changes that arrive in waves, some fast and subtle, some slower and heavier, and most of them happening in regions we cannot see, only measure. The point of telling this as a timeline is not to make it frightening, it is to make it legible. Because when you can picture how it unfolds step by step, it stops feeling like chaos and starts feeling like weather, a kind of weather that happens in space. And like all weather, it has gradients, uncertainty, and a rhythm that can be understood. A coronal mass ejection, often called a CME, is a large release of plasma and magnetic field from the Sun's outer atmosphere, the corona. Plasma is a gas so energized that electrons are stripped from atoms, leaving charged particles that respond strongly to magnetic forces. The Sun is full of plasma. In fact, the Sun is mostly plasma. What makes a CME special is that a massive, coherent cloud of this charged material is thrown outward, carrying with it a magnetic structure that can remain organized across millions of kilometers. You can imagine it like a bubble, or a wavefront, or a billowing storm cloud, but made of charged particles and invisible field lines. It is not the same as a solar flare, though the two can occur together. A flare is a sudden burst of electromagnetic radiation, including X-rays and ultraviolet light traveling at the speed of light and arriving at Earth in about 8 minutes. A CME is slower. It is matter, not just light. It travels through interplanetary space, riding the solar wind, sometimes pushed faster by its own internal pressure, sometimes slowed by the medium it passes through. Depending on speed, it can take 1 to 3 days to arrive, sometimes a little more, sometimes less. That travel time is the quiet interval where forecasters watch, revise and prepare. Because the CME may be aimed toward Earth, but the exact strength of its impact depends on details that are hard to know until it is almost here. The timeline begins before anything reaches Earth, at the moment the Sun releases the CME. On the Sun's surface, magnetic fields can become twisted and stressed, especially around sunspots and active regions. The Sun rotates, plasma flows and magnetic loops can become tangled like cords. Sometimes the tension builds until the configuration reorganizes suddenly. The rearrangement can unleash a flare, and it can also eject plasma outward as a CME. Solar observatories, both on the ground and in space, watch the Sun in different wavelengths, and some instruments are designed specifically to see the corona. In those images, a CME can appear as an expanding halo, or a bright front moving away from the Sun. When it looks like a halo surrounding the Sun in the instrument's field of view, that is often a sign the CME is coming toward or away from Earth, because we're looking down the barrel of its expansion. This is when the first estimates appear. Analysts infer an initial speed, a likely direction, and an approximate arrival window. The early message is usually cautious, possible arrival in a day or two, possible geomagnetic storm conditions depending on magnetic orientation. At this stage, the biggest uncertainty is not whether a disturbance will occur, but how strongly the CME's magnetic field will couple to Earth's magnetic field. Now imagine the clock starting. We can call this moment hour 0, the moment the CME leaves the Sun in a form that instruments can see. From hour 0 to about hour 1, the CME is still close to the Sun, and the information available is mainly about its size, its apparent speed in the plane of the sky, and its general direction. The CME's internal magnetic structure is not directly measured at this distance. It is inferred sometimes from the way the eruption looks, and from the magnetic complexity of the source region. but inference is not certainty. During this first hour, forecasters might produce a first arrival estimate, perhaps saying a window like late tomorrow or early the next day. They might also indicate whether the CME appears fast, which increases the odds it arrives sooner and produces a stronger shock. A fast CME is not automatically a devastating one, but speed increases kinetic energy and can amplify the compression of Earth's magnetosphere when it arrives. Speed also affects how strong the shockwave in front of the CME might be, because a fast CME can plough through the solar wind like a boat creating a bow wave. Between hour 1 and hour 6, the CME moves farther from the Sun, expanding as it
Voltage
goes.
fluctuation in the
Think of
western
it as a
sector
bubble that
stabilized.
grows as pressure drops. The
Monitoring
cloud
the
becomes
flow.
larger, its internal density decreases, and it starts to interact with the ambient solar wind. Sometimes the CME remains relatively intact, travelling like a coherent structure. Sometimes it evolves its shape, distorted by variations in the solar wind or by interactions with other solar outflows. If there were earlier eruptions, the CME may travel through a region already disturbed, which can change its speed and its eventual impact. During this period, modelling becomes important. Forecasters run propagation models that use the observed speed and direction to predict arrival time. These models can give a range, and the range can shift as new measurements refine the initial conditions. This is often when the public sees a phrase like watch or advisory. It is not a sign of panic. It's a sign that the probability of geomagnetic disturbance is elevated enough that operators of sensitive systems should pay attention. Now, while the CME travels, something else can happen almost immediately, arriving at Earth in minutes. If the eruption includes a strong flare, the flare's electromagnetic radiation can increase ionization in Earth's upper atmosphere on the day side, particularly in the D layer of the ionosphere, which can cause shortwave radio absorption. This is one of the earliest impacts in the overall story because it arrives at the speed of light, but it is not the CME's direct impact, it is the flare's radiation. If the flare was significant, you can imagine a quick change in the ionosphere, like a curtain becoming denser for a while. High-frequency radio users may notice increased fading or blackout on certain paths. Aviation and maritime communication
CME
systems that rely on
not
HF
yet
can be
measurable
affected
at
in
L1.
specific
Quiet
regions.
waiting.
For most people, it passes unnoticed. But for those who use these frequencies, it can be the first hint that something on the Sun has changed the environment around Earth. This flare-related effect can last minutes to hours, depending on the flare's intensity and the state of the ionosphere. Then it often subsides, leaving a quiet interval before the CME itself arrives. As we move into the first full day after hour 0,
Trajectory
from about
deviation
hour 6
detected
to
on
hour
sector
24,
gamma.
the
We have to abort the burn.
CME is in
Confirmed.
transit, and the
Cycling
story
to standby
becomes one of
sequence.
anticipation and refinement. Upstream solar wind monitoring spacecraft positioned between Earth and the Sun continue to measure the background solar wind, but they cannot measure the CME's core until it reaches them, and these spacecraft are much closer to Earth than the CME is during most of its journey. So the day is filled with updated arrival estimates rather than direct measurements of the incoming magnetic structure. This is the phase where uncertainty feels largest. Forecast models might say arrival in a 12-hour window. That window may narrow as time passes. Meanwhile, operators of satellites might prepare not by shutting everything down, but by reviewing procedures. Satellite operators may postpone sensitive maneuvers, ensure protective modes are ready, and increase monitoring. Power grid operators in high-latitude regions may place staff on alert and review the condition of key
24
transformers.
approaches. CME
Aviation
faster
route
scenario
planners may
implied.
watch space
Distance
weather
closing.
advisories, especially for polar routes where communications and radiation conditions can be more sensitive during geomagnetic storms. The world does not stop. It does not need to. It simply shifts into a posture of attention. Somewhere in this first day, a quiet but crucial idea enters the story. Earth's magnetosphere is not harmed by the CME like a physical object hitting a wall. Instead, it is pressed and reshaped by the flow of solar wind and the embedded magnetic field. The magnetosphere is Earth's magnetic environment, a protective region formed by Earth's internal magnetic field interacting with the solar wind. On the day side, it is compressed. On the night side, it extends in a long tail. When a CME arrives, the pressure increases. The magnetosphere compresses more strongly. Currents intensify. If the CME's magnetic field has a southward component relative to Earth's northward field on the day side, magnetic reconnection can occur efficiently. Reconnection is like a gate opening between the solar wind's magnetic field and Earth's, allowing energy and particles to enter Earth's system more readily.
Roger that.
This southward orientation is often what turns a moderate arrival into a stronger geomagnetic storm. And it is the part that is hardest to know in advance, because the CME's internal magnetic orientation is not fully measured until it's close to Earth. As hour 24 approaches, the sense of soon becomes more real. A fast CME might arrive around this time. A slower one might take longer. The timeline now depends on the CME's speed. Let us imagine a common scenario where the CME arrives between 1 and 2 days after launch. The next major marker is the arrival of the shock front. Many CMEs have a shock wave in front of them, especially if they are fast. A shock front is a sudden jump in solar wind speed, density, temperature, and magnetic field strength. It is the first physical boundary Earth encounters. This is the moment when upstream monitoring spacecraft detect the event directly. These spacecraft sitting roughly 1.5 million kilometers upstream from Earth are like a buoy in a river. When the CME's shock hits the buoy, measurements change abruptly. Density spikes, speed increases, the magnetic field strengthens. This is a clear sign the CME has arrived in Earth's neighborhood. And because the spacecraft is upstream, there is a short lead time before those conditions reach Earth itself, often on the order of 30 to 60 minutes, sometimes a bit more, sometimes less, depending on solar wind speed. This lead time is the final window where forecasters can move from broad estimates to immediate warnings. It is also when the most critical unknown, the magnetic orientation, begins to be measured. The data stream shows whether the magnetic field is turning southward and how strongly and for how long. Now imagine the timeline at the moment the shock reaches Earth. This is the start of the main impact phase. The magnetosphere is compressed. This compression can be measured as a sudden increase in geomagnetic indices and a sudden change in the position of the magnetopause, the boundary between Earth's magnetic field dominance and the solar wind. In strong compressions, the magnetopause can move inward sometimes enough that satellites in higher orbits may briefly find themselves in a different plasma environment. This can affect satellite charging conditions. The shock itself can also energize particles in near-Earth space and disturb the radiation belts. The first consequences are again subtle and technical changes in satellite environment, increased risk of anomalies, and increased monitoring. But there is also a visible consequence that can arrive later: aurora. Aurora is created when charged particles guided by Earth's magnetic field lines collide with atoms and molecules in the upper atmosphere, causing them to emit light. Under quiet conditions, aurora is mostly confined near the poles. During geomagnetic storms, auroral activity can expand toward lower latitudes. The shock's arrival does not instantly create dramatic aurora everywhere. Instead, the storm evolves. If the magnetic orientation remains favorable for reconnection, energy continues to pour into the magnetosphere and ionosphere, and aurora can intensify and spread. People might see it hours into the storm's main phase, especially if the storm reaches moderate or strong levels. For many, it is the only visible sign that anything is happening. A green shimmer in the sky, perhaps red at higher altitudes, a quiet curtain of light moving slowly like breath. It is easy to see aurora as pure beauty, and it is. But it is also a sign that Earth's space environment is energetically disturbed. Now let us return to the core promise of tonight's story, a timeline of impact, and specifically what arrives first. After the shock, the first broad category of impacts tends to involve radio propagation and navigation systems because they rely on the ionosphere being stable. When the CME drives geomagnetic activity, the ionosphere can become turbulent with irregularities in electron density. These irregularities can cause scintillation, a rapid fluctuation in radio signal amplitude and phase similar to how stars twinkle through a turbulent atmosphere. For satellite navigation signals, scintillation can be a problem. The receiver may struggle to maintain lock on the signal. Position accuracy can degrade, especially for high-precision systems. The effect is not always uniform across the globe.
Conjunction predictions
It depends on local
Many
time
orbit tracks
latitude and
wiggle
storm
slightly.
intensity.
Calm.
High latitudes are often more affected, and equatorial regions can also experience strong scintillation under certain conditions. The earliest noticeable issues for the public might be
Adjusting
smaller
the window
navigation
now,
app
tracking
that
the
seems
slide.
slightly less accurate. A moment where a
Window
location
locked in new
marker
position.
drifts.
Acknowledged.
For critical services, the concern is greater. Aviation navigation, maritime operations, precision, agriculture, surveying, timing, synchronization for networks, all can be influenced by ionospheric behavior. During moderate storms, these impacts are usually manageable and localized. During stronger storms, the impacts can be more widespread. This is one of the reasons storm watches matter. They prompt operators to be ready for degraded performance and to use backups if needed.
Check the trajectory
While
on
navigation and
satellite
radio
12.
are dealing with an altered
Running
ionosphere,
diagnostics.
satellites in low Earth
Signal
orbit
restored.
face another
It's
effect,
stable.
atmospheric drag. When geomagnetic activity heats the upper atmosphere, it expands upward, increasing density at altitudes where satellites fly. Even though the density is still extremely low, satellites move fast and drag matters. Increased drag causes satellites to lose altitude more quickly. Operators may need to adjust orbits. During significant storms, the increased drag can also complicate tracking and conjunction predictions, which are used to avoid collisions between satellites and debris. For large satellite constellations, this becomes a busy time. Some satellites may enter protective modes.
Then southward again.
Ground controllers watch for
Reconnection
anomalies.
resumes.
Most
Stronger.
satellites are designed for these
Calm.
environments, but the risk is elevated. The earliest breaks in satellite systems are often not permanent damage, but operational disturbances, brief outages, increased errors, occasional safe mode transitions. From the user's perspective, it can appear as a momentary service hiccup. From the operator's perspective, it is a period of heightened vigilance. As the storm continues, another layer of impact
The forecast
emerges in the
update
form
shows
of
this gentle glow
geomagnetically induced
expanding
currents,
across the
often
central state,
abbreviated in technical
signifying continued
contexts.
calm
When
weather
Earth's
and clear
magnetic
skies.
field changes rapidly during a storm, it can induce electric fields in the ground. Those electric fields can drive currents in long conductors like power transmission lines. These currents are not the alternating current the grid is designed to carry. They can enter transformers and push them towards saturation, causing heating and producing harmonics that can confuse protective systems. This is the part of space weather that reaches the ground in a more tangible way, and it is often what people fear most. But it tends not to be the first effect because it requires a sustained and strong geomagnetic disturbance. Power grids also have protections and operational procedures, and grid operators monitor conditions. During a stormwatch grid, operators may reduce stress, adjust configurations, and monitor key equipment. In many cases, these actions prevent serious outcomes, but in stronger storms, the risk of transformer
minor
heating and
trips.
line trips increases,
One line
especially
dims
in high
briefly,
latitude
others
regions with certain
compensate.
ground conductivity conditions and long transmission lines. If enough lines trip in an
Cascades are
unfavorable
rare.
sequence,
The grid
cascading
holds.
outages become possible.
Steady lights remain.
This is rare, but it is not imaginary. It is part of why space weather is treated as a legitimate risk. In a timeline, power grid issues, if they occur, often appear during the peak storm period rather than at the very beginning. They are a later wave arriving after the ionosphere is already disturbed and after satellite operators are already responding. Now, to make the timeline feel more real and less abstract, we can walk through an imagined but realistic sequence of hours once the CME arrives, using gentle time markers rather than sharp lists.
Most people
Imagine
notice
the
nothing.
shock arrives in the early evening local time somewhere on Earth. In the minutes after
Just a
upstream
fluctuation in
monitors have
sector
already
gamma.
shown the jump,
Compensating now.
forecasters issue an immediate alert the shock has arrived, geomagnetic activity is increasing. The magnetosphere compresses. Satellites register the change in plasma environment. In the first hour, auroral activity begins to brighten at high latitudes. Communications at high frequencies become less reliable on polar paths. Over the next 2 to 3 hours, if the CME's magnetic field remains southward, for sustained periods reconnection continues. Energy flows into Earth's magnetosphere. The ring current intensifies a circulating current around Earth that is associated with geomagnetic storms. Indices that measure geomagnetic activity rise. The ionosphere becomes more irregular. GPS scintillation becomes more likely in certain regions. The auroral oval expands. People in places farther from the poles might begin hearing that aurora could be visible. If the storm reaches moderate levels, the aurora can become a public spectacle, but even then it may appear as a faint glow to the naked eye, much more vivid to cameras. As the storm reaches its peak, often several hours after the shock, the question becomes not whether there is a storm, but how strong it will get and how long it will last. A CME can have a complex internal structure. The magnetic field can fluctuate, turning southward and then northward, strengthening and weakening. The duration of southward field is critical. A brief southward interval may produce a modest storm. A long, strong southward field can drive a stronger storm. This is why forecasts are updated in real time during the event. It is not like a hurricane making landfall where you can see the eye wall. It is an invisible magnetic storm, and its intensity is measured in data streams and indices rather than in wind and rain. Still, it has a rhythm. There is a sudden onset at shock arrival, then a main phase where geomagnetic activity builds, then a recovery phase where currents weaken and the system returns toward quiet. The main phase can last
deviation
hours.
Detected on sector gamma.
The recovery can last a day or more.
Confirmed.
During the
Cycling to
main
standby
phase,
sequence.
satellite drag can increase because the upper atmosphere is heated. This heating does not happen instantly everywhere. It is driven by currents and energy deposition at high latitudes that then alter global circulation patterns in the upper atmosphere. The result can be a global change in density at certain altitudes. Satellite operators monitor predicted drag changes and adjust planning. In extreme storms, the density increase can be substantial enough to cause noticeable orbital decay in a short time. Again, most of the time, this is an operational inconvenience rather than a catastrophe, but it is a real physical effect of space weather. Meanwhile, the ionosphere may produce not just scintillation, but broader distortions, including changes in total electron content that affect radio propagation. Navigation systems that apply ionospheric corrections can still function, but accuracy may degrade.
CME faster scenario
Certain
implied.
ground-based
Distance
augmentation
closing.
systems may see reduced performance. Systems that rely on precise timing derived from navigation signals may depend more on internal clocks during periods of degraded reception. In well-designed systems, redundancy and holdover capabilities keep operations stable. In less robust systems, small timing issues can cause more noticeable coordination problems. The earliest public-facing symptoms, if any, tend to be small intermittent radio issues, occasional satellite service disruptions and unusual aurora reports. The deeper impacts remain largely behind the scenes in control rooms, where operators watch graphs, not skies. Now let us also address the psychological timeline, because it matters for understanding headlines. When a CME is announced as headed toward Earth, it can feel like the event is locked in. But in reality, headed toward Earth often means that models suggest Earth is in the path, not that the exact center of the CME will strike Earth directly. A CME can glance Earth or hit more squarely. A glancing blow might produce a mild storm. A direct hit with strong southward magnetic field might produce a
Critical
stronger
deviation
one.
detected on sector gamma.
This is why
Reroute auxiliary
forecasts
power
include
now.
probabilities and ranges.
Executing reroute
The
protocol.
timeline
Stand by
contains
for
uncertainty
stabilization.
by nature.
Confirming telemetry lock on
That
satellite
uncertainty
5.
is not
Rerouting auxiliary
incompetence.
power now.
It is a reflection
Stay
of
calm. We have
complexity.
this.
The Sun-Earth system is a dynamic plasma environment, and measuring a CME's internal magnetic orientation far from Earth is challenging. The best certainty arrives only shortly before impact when upstream monitors measure the field directly. That is why you sometimes see forecasts change quickly near arrival. It is the moment when the last crucial unknown becomes known. As the main phase fades and the recovery begins, the timeline enters a quieter stretch. The magnetic field variations slow. The induced currents in the ground diminish. The ionosphere becomes more stable. GPS performance improves. Satellite operators continue to assess any anomalies and adjust orbits if needed. The aurora may remain visible for a while, especially if the storm was strong and the recovery is slow, but it tends to retreat toward higher latitudes as the system calms. The recovery phase can be long because the magnetosphere's energized populations of particles and currents take time to dissipate. It is like a bell that rings long after the strike. During recovery, the environment may still be more active than usual and smaller substorms can occur, but the intensity generally declines. This is the overall timeline, but there is another layer that makes it even more interesting. Not all CMEs arrive alone. Sometimes the sun releases multiple eruptions in a short period. If a second CME follows the first, it can travel through the disturbed solar wind created by the first, potentially reaching Earth faster. Two CMEs can interact, merging or altering each other's structure. This can amplify effects or create unexpected timing. In such cases, the timeline becomes a braided stream rather than a single wave. Forecasters watch for these interactions because they can change arrival estimates and intensities. The sun in active periods can behave like a stormy ocean with overlapping swells. Earth's magnetosphere responds to the combined pattern of pressure and magnetic orientation. In a braided event, the storm may have multiple peaks. The system may be driven hard, then briefly relax, then driven again. The aurora may brighten, fade, then brighten again. The ionospheric disturbances may wax and wane. This is why space weather can feel unpredictable to outsiders. But to those who study it, the unpredictability is structured. It follows physics. It follows magnetic geometry. It follows the way energy flows between star and planet. Now, because this is deep space sleep, we can take a calmer step back and let the timeline become a gentle narrative of a planet being touched by its star in an invisible way. Earth is not isolated. Earth is immersed in the solar wind. The magnetosphere is a protective shape that changes continuously. Most of the time, this interaction is quiet and we forget it exists. A CME is a moment when the interaction becomes louder, not in sound, but in electromagnetic activity. It is like the difference between a calm sea and a swell passing through. The sea is still the same sea, the planet is still the same planet, but the energy level changes and systems that depend on stable conditions must adapt. So if we compress the story into a gentle, realistic timeline, it feels like this. In the first minutes, if there is a flare, the dayside ionosphere responds quickly and radio conditions can shift. Over the next day, the CME travels through space while forecasts refine. In the hour before arrival upstream, monitors detect the shock and measure the magnetic field, giving the most immediate warning. At impact, the magnetosphere compresses and the storm begins. Within the next few hours, the ionosphere becomes disturbed navigation, and radio propagation can degrade, aurora intensifies, and satellites experience elevated risk and increased drag. If the storm is strong, induced currents can stress power systems during the peak. Then over the next day, the system recovers, gradually returning toward quiet. But a timeline is not only about what happens, it is also about what does not happen and why. Many people hear about CMEs and imagine that a single event will shut down the world. That can happen in extreme scenarios, but it is not the typical
Conjunction
outcome.
predictions harder.
Most
Many orbit
CME-driven
tracks
storms
wiggle
produce
slightly.
manageable
Calm.
disturbances. The reason is not luck alone. It is also the result of preparation and engineering. Satellites are designed with radiation tolerance and protective modes.
Adjusting the window
Navigation
now,
systems
tracking the
have
slide.
error correction and redundancy. Grid
Window
operators
locked in new
monitor and
position.
respond.
Acknowledged.
Space weather agencies issue alerts. The entire point of a watch or warning is to reduce vulnerability through awareness. The timeline is not a countdown to disaster, it is a sequence that allows mitigation. There is also a quiet beauty in the way this all connects to things we have known for a long time. Long before satellites people saw aurora and felt awe. Long before we named CMS Earth's magnetic field was being disturbed by solar activity and compasses sometimes behaved strangely.
Check the trajectory on satellite 12.
The planet has always
Running
been in
diagnostics.
conversation with the sun.
Signal
What is
restored.
new is
It's
that
stable.
we've built a civilization that extends into space and relies on signals passing through the upper atmosphere. We have become more sensitive. The timeline of impact is, in a way, a timeline of how modern life is connected to an ancient star. Now, as we near the end of our journey for tonight, let the story slow and settle. Imagine the CME as it continues outward, past Earth after the encounter. It does not stop here. It travels on expanding thinning, eventually blending into the background solar wind. Earth remains behind, still orbiting, still turning, still protected
Then
by its
southward
magnetosphere.
again.
The storm
Reconnection
fades,
resumes, stronger,
the aurora
calm.
retreats, signals stabilize, satellites resume normal operations, the power grid remains steady or returns to normal, and the data collected during the event becomes part of future understanding. Every CME is not just a disruption, it is also a measurement opportunity. It teaches scientists about reconnection, about particle acceleration, about the coupling between the magnetosphere and
The forecast
ionosphere,
update shows
about the
this gentle
complex
glow
behavior of the
expanding
upper
across the
atmosphere,
central
about the
states,
resilience of
signifying
engineered
continued
systems.
calm weather and clear skies.
The sun sends a wave and Earth answers, and we learn by listening. So if you ever see that headline again, the sun just fired a CME toward Earth, you can let it translate into a calmer truth. You can imagine the timeline like a slow tide rather than a sudden crash. You can picture the first light speed effects if a flare occurred, the long day of travel and refinement, the sudden shock arrival at upstream monitors, the half-hour warning, the compression of the magnetosphere, the building of the storm, the aurora spreading the ionosphere, becoming irregular navigation, and radio becoming less certain. For a time, satellites feeling drag, and only in stronger cases the ground-based currents that can stress power systems. Then the long recovery, the quiet return. This is what it looks like when the sun's weather reaches Earth, not a single moment but a sequence, a timeline, a story written in fields and
If minor
particles and the
trips.
soft glow of
One
night
line
skies
dims
that
briefly,
occasionally
others
brighten
compensate.
far from the poles.
Calm.
And now, as we let the timeline drift into silence, you can take the most calming
Cascades are
thought
rare.
from it.
The grid
The universe
holds.
is not random.
Steady lights remain.
Even the storm has structure. Even the disturbance follows rules. The sun, active and restless, sends out these vast clouds, and Earth, shielded and stable, absorbs them, bends them, redirects them, and continues on. Our technology may feel the edges of the event, but the planet itself remains turning steadily beneath the stars. Thank you for spending this quiet journey with Deep Space Sleep. If you want to continue drifting, you can imagine the solar wind flowing past Earth like a river
Most
of
people
lightless air.
notice
The
nothing.
magnetosphere holding its shape like a quiet bow wave, and the distant sun continuing
Just a fluctuation
to
in
shine
sector
warm
gamma,
and far
compensating
away,
now.
while the night here remains calm, wide, and safe enough to rest.